It is section 1.3, computer arithmetic and convergence. Numbers are saved with an approximation by either rounding or chopping. It is particularly true for real numbers. Integers are saved in 4 bytes, which is same as the 32 bits, and floating point numbers are in 4 bytes, and doubles are in 8 bytes, 64 bits. And earlier days, the machine precision was quite critical, but nowadays, double is default for most computers, and you can achieve even higher precision. So considering the machine precision for modern computers is not really important. However, here we'll see one example. In Maple, default precision is 10 digit. Here, float point number evaluation of pi is given here, and 8-digit precision, and here 16-digit precision. We try to get here the 10-digit precision times and 8-digit precision minus 16-digit precision of pi, then we can get such a result. However, pi times pi minus pi must be 0. So here, if your machine precision is not good enough, then you have to be very careful. However, for most cases, along with the modern computers, you don't have to worry about too much around the machine precision. Okay, P star is approximation of P, then the absolute error is defined to be P minus P star in modulus, and relative error is now obtained by dividing by P, the true value. Once the P is large or small, like around 0 or very large in modulus, then relative error is more relevant. For instance, is around the 10 to the 6th level, and the error about 10 to 3 is quite small compared with the magnitude of the solution. However, the magnitude of P is about 10 to the minus 5. Now, if the error is about 10 to the minus 4, then the error is 10 times larger than the true value. So it is really, even though the error is 10 to the minus 4, is very poor approximation. So that relative error is more relevant. Okay, that is significant digits. This is not really significant, so we'll skip here. An algorithm is a procedure that describes a finite sequence of steps to be carried out in a specific order, but the description manner must be unambiguous. And this algorithm can be effectively expressed by using pseudocode. If small change in input is making small change in output, then the algorithm is called stable. Otherwise, it is called unstable. Some algorithms are stable only for some conditions. Then it is called conditionally stable. If you try to get the solution iteratively, or if you compute step by step, then an initial error may be propagate, and also each time the error must be accumulated, so that en and n step later can be increasing. Now, once the manner of increasing is given in this way, the initial error times n along with some constant c, then now we can say that the error is increasing linearly, so that the growth of the error is linear. And usually, in this case, the algorithm is stable. And in some cases, the initial error is multiplied by a number larger than 1, so that eventually in nth step the error is exponentially increasing. So in this case, the growth of error is exponential, and the algorithm is unstable. Now, we define here rates of convergence or orders of convergence. Now, xn is a sequence and converging to x star. Now, later error, and this is early error, and there's a later error. And later error is bounded by here earlier the current error times C1, which is less than 1. So it is decreasing, but the manner is linear. So in fact, there's a power over the 1. So in this case, we say that the rate of convergence is at least linear, or just simply linear. Now, rather than C1 a constant, if we can find epsilon n, which is approaching 0, then here is faster than linear, so that we say the convergence is superlinear. Now, if we can find the square, so that later error is way smaller than the current error, and for instance, this is now 10 to the minus 2, then squared is 10 to the minus 4, and here, even though some constant c is larger than 1, if the quantity is moderate, then anyway, this quantity will be around 10 to the minus 4, so that the error is reducing quadratically, and we say the convergence is quadratic. In general, we can define the convergence rate of alpha in this way. So if you can find alpha, which is larger than or equal to 1, then here we say the convergence rate is alpha. Now, once alpha is 1, then this c must be less than 1. If larger than 1, then along with this alpha is 1, and there's no guarantee to get convergence, so that the definition is not meaningful, right? Let's see this example. Consider a sequence defined recursively as x1 is 2, and from x2 the numbers are defined recursively by using this equation. And here, part A, find the limit of the sequence, and part B, show that the convergence is quadratic. To show, to find the limit, first of all, you have to show that it is convergent. Now, practically, once you try to get, for example, x2 then x2 is same as now x1 over 2. x1 is 2, 2 over 2 plus 1 over 2. So that this is 3 over 2 and x3, and along with that, and you can find x3. You'll see that here x1, x2, x3, these are a decreasing sequence. And also mathematically, we can prove that xn is decreasing. And also, we can prove that for all xn, and here is larger than square root of 2. And here, that is now, hint is given so that you can prove this one. Okay. Now, xn is decreasing sequence and bounded below, so that it cannot be smaller than square root of 2, so that somewhere the sequence should stop, which means that the sequence is convergent. So here, and xn plus 1 will converge to x star. xn also will converge to x star. So that for part A, now once it is convergent, then let's say the limit is x star. Okay, let's say x. Okay, for simply we say x, then that will become x in the limit, and then right hand side, okay, x over 2 plus 1 over x, right? If we multiply 2x, then 2x squared equals now x squared plus 2. So 1x squared will be cancelled, so that x squared equals 2, which implies that x is plus minus square root of 2, but is larger than square root of 2 for each one, and the limit will be square root of 2. So we found the limit. Now for part B, we have to show that the convergence is quadratic. Okay, let's see the definition of quadratic convergence. So once this inequality is satisfied, then the convergence is quadratic. We'll start with this part. Now, rather than x star, we are using x value here. Okay, now x n plus 1 minus x star, which is now square root of 2. What is this one? This one is here, xn over 2 plus 1 over xn. Now, minus square root of 2. Here we'll try to put out 1 over 2 xn. Then for the first one, that will become here xn squared, and second one will be 2, and the final one will become 2 square root of 2 xn. Okay, we'll rewrite this one here, 1 over 2 xn. And then, okay, that one is now, okay, xn squared, and we write down this one first, and minus 2 square root of 2 xn, and for these two, we write here that is square root of 2 squared, like that. And then, that is now a squared, and b squared, there is a 2ab minus 2ab, so that inside the bracket, that is a minus b squared. So that is 1 over 2xn. That is a is xn. Now b is square root of 2 squared. Right? Now we are taking, now we'll try to make this form by using absolute sign, absolute notation. The absolute value of xn plus 1 minus square root of 2 is now same as that. now here, xn is for all n is larger than square root of 2. So that this term is smaller than 1 over 2 square root of 2, right? And for this term, we say xn minus square root of 2 squared. So that exactly this one is what we needed here. The later error is bounded by constant times earlier error squared. This one is bounded by this constant times earlier error squared. So it is quadratic convergence, right? Big O and little o notation. Okay, a sequence alpha n is in big O of beta n if there is a positive number k such that now alpha n in modulus is bounded by k times beta n modulus for large n. That one is equivalent to be here alpha n over beta n. The absolute value is bounded by k for large n. And also limit, okay, we may say this one also in this way. Limit as n approaches infinity alpha n over beta n is now here, that is now k, or less than or equal to k. Either way we can write. Okay, then here we say alpha n is in big O of beta n. So alpha n is in big O over beta n, so that we are using here inclusion notation, or we can ignore in here, then alpha n is big O over beta n. In this case, we are using equal sign, alpha n equal here big O over beta n. Now, for little o, here, if there is a sum, now sequence epsilon n, and which is converging to 0, and satisfy this inequality for large n, then we say alpha n is in little o of beta n. Equivalently, here divided by beta n, now as n approaches infinity, this value will go to 0, so that now if this is satisfied, then is here now we are using little o notation. So here alpha n is in little o over beta n, and we can use this notation, or ignoring in here again, we can use equal sign. Okay. Let's try to solve this problem. Fn given here is in big O of n to the minus 2 and little o of n to the minus 1. We'll try to solve only this portion. Now Fn, so that for big O portion, okay, that one, here Fn over now n to the minus 2. That can be written here again n squared and n plus 3 and divided by n cubed plus 20 n squared. Right? This is always bounded by 1 and also approaching 1, so that it is approaching 1, but and also is always bounded by 1. Okay. So there is a positive number k such that for large n, this quotient is now bounded by 1. That's k, so that we can say that f of n is in big O of n to the minus 2. Right? How about little o portion? Now here f of n over n to the minus 1, which can be rewritten here n plus 3 over n cubed plus 20 n squared. Now this is cubic and that is quadratic, so that it is approaching 0. Right? So it is satisfying that portion. So we can say that f of n is in little o of n to the minus 1. Right? Okay. Now that is for n goes to infinity. And now here we can define a big O and little o for convergence. And now assume here in the beginning g of h is converging to 0 as h goes to 0. Now f of h is in big O of g of h if a positive number k exists, so that here f of h over g of h is bounded by k for h sufficiently small. Now h is approaching 0, so that you have to take this quotient bounded by k for h sufficiently small. And little o is also can be defined similarly. Once this quotient approaches 0 as h approaches 0, then now we have to use a little o notation. Right? Okay. Here, let's see this example. If we make a Taylor expansion for cosine x, then we can get that. Now, by using computer algebra software, for example, Maple, we can get such result. Now, cosine x, Taylor expansion about 0, and along with 4 terms, then it is producing that result. Now, and compared with the original Taylor expansion, we can see that this portion is considered as big O of x to the 4. Right? Now, we'll check if really this is big O of x to the 4. Now, if we define this as f of x, then f of x divided by x to the 4, then we can get this one. Now, this is alternating series, positive term, negative term, but each one, now, once x is small, around the 0, then these terms are decreasing and alternating. Then that the series is bounded by the first term, so that is bounded by 1 over 24. So the quotient is anyway bounded by a positive number, so that we can say this part is in big O of x to the 4, right? Okay, choose the correct assertions. Okay, for each one, we say n approaches infinity. Okay, for that one, to check if this assertion is correct, we have to make this one over that one, so that here n squared plus 1 and over n cubed and over and 1 over n. Okay, for that one, if we rewrite then now here n can be multiplied over there, so that n squared plus 1 over n cubed. And it's larger than 1, however, it is approaching 1. For large n, we can say this is bounded by 2, but not approaching to 0, so that here is this term is in big O of 1 over n, because here little o is used. This assertion is wrong. Right? Similarly, you can check the others, and in fact, for this one here, correct one is D. Okay. Now we have to determine the best integer k in the following equation. Okay. Now, okay, once you try to make here the derivative, then derivative of arctangent is 1 over 1 plus x squared. Now x is approaching 0, so that we can make this one here infinity series is 1 minus x squared plus x to the 4 minus x to the 6 plus like that. And now this is convergent when x value is bounded by 1. Okay, so we know that. Now from this one we are taking integration. Then now there is arctangent of x, and this is same as x minus 1/3 of x cubed and plus 1/5 of x to the 5 and so on, right? So that here there's x here. Now for remainder part, that one is in big O of x cubed, right? So k must be 3. Okay. And yeah, k must be 3. And this is one way of solving this problem. Now, you may solve this problem another way. Okay, this is number 1. And another way, you may think in this way. Now, arctangent of x, now minus x, we are moving this one to left-hand side. It's now same as big O of xk. So that by using the technique, the definition we considered, here we try to find the k such that now the quotient arctangent of x minus x over x to the k, and as here now we may take the limit x approaches 0, but anyway we have to choose k such that this quotient for very small k, quotient is bounded by some number. Then, so that the major question is we have to find this k. You may start with case 1, and then you'll see that here, and if you choose this some different k from 3, then this quotient may blow up or converge to 0. Only when it is 3, then you will see that here this is bounded by a constant. Okay, so you can solve the problem in this way. Either way, you can solve the problem. Here, f of h is defined in this way. What are the limit and the rate of convergence of f of h as h approaches 0? Okay, what is the limit? Okay, And first of all, the limit h approaches 0, and here 1 plus h minus e to the h over h. Now, bottom and top are approaching 0. So by using L'Hopital's rule, we can get the limit. The same limit, h approaches 0. Derivative of top is same as 1 minus e to the h, and bottom is 1. Now, h approaches 0, then top is approaching 0, so that there is 0. So the limit of f over h is 0. Now, here, second portion, and we have to find the rate of convergence of f of h. And it's asking to find the k, and such that here f of h is now big O of h to the k. So it is asking to find k. So here, let's do it. Now, f of h, which is 1 over h, now 1 plus h minus e to the h over h to the k. So we can rewrite this one in this way, 1 plus h minus e to the h, and here h to the k plus 1. Now, for this one, once h approaches the 0, then bottom and top are approaching 0. So that, again, by using L'Hopital's rule, we can reach at here 1 minus e to the h, right? And divide by here, now k plus 1 coefficients, and h to the k, right? Okay. Now, again, once k is, for example, now 0, then it's approaching 0. So that now we have to find k such that this one is approaching to non-zero and not blowing up. So here we have to assume that k is larger than or equal to 1. Then it's 0, and again it becomes 0. Now we apply one more time of derivative. Then there is now minus e to the h, and bottom is now k plus 1, and k, and now h to the k minus 1. Okay, here top is approaching minus 1. Okay, that is now a constant, and it cannot be 0. So it must be constant. Now h is approaching 0, so that this k minus 1, if k minus 1 is now positive, then this will go to 0, so that the value, the quotient will blow up. So it is not allowed. So k minus 1 must be 0, which means that now k must be 1. Okay? So here we conclude that f of h is in big O of h. Okay? Now, for this problem, you can do it yourself. And for this one, it's a little bit complicated. Now, we already know an is approaching 0, and lambda is larger than 1. For this summation, now n is approaching infinity. Only here, what we know is an is becoming smaller to become 0, but now lambda is larger than 1, so that here kth power, so for extra term, here last term is lambda to the n, so larger than 1, so that is exponentially growing. Now, for this summation, n goes to infinity, we can figure out that this whole thing is little o lambda n. Once it is divided by lambda n, then it is approaching to 0. So we can prove that. And here the hint is given. Now, if you are interested in this problem, then try to solve it yourself. Okay, this is end of the section. Thank you.